So I'm very happy to restart this Zoominar, and I have the pleasure to introduce Georgios Dimitroglou Rizell, who will talk to us about Hamiltonian classification and unlinkedness of fibers in cotangent bundles of Riemann surfaces.
Thank you very much. It's a pleasure. I would have preferred to be in Montreal, but yeah, this is also great. Thanks for the opportunity.
In Montreal or in Princeton or in Tel Aviv or in Paris.
Ah, right. This is the joint. I would have loved to go to all places.
That's right.
Sorry about that. And there seems to be a typo in my title, but I don't think. Unlikeness. No. Anyway. So this is joint work with my collaborator Laurent Coté, and you can find it on archive. I put the number there. It's called rigidity in the title instead of Hamiltonian classification. But I tried to find a title that will suit my talk a bit better. So tell me if you have any questions during the talk, and feel free to ask me things, and or if I'm not, if the technique is not, if the technology is not working as it's supposed to, then also tell me, because it's the first time I use this app in this computer for a talk. So anyway, I will give some brief introduction. I will then move on to some results, and then I will go on to kind of put this into perspective with some differential topological questions. And this could have been in the introduction too, but I wanted to move on a bit quickly to the results. So C number 2 is some kind of motivation or outlook for what could be true in high dimensions. But in fact, the results are all in dimension 4, because the techniques are such that you all can reach conclusions in dimension 4. And then I will end with talking about the proof a bit. So that's the plan. So let me now try to see here. Yeah, so let me scroll down here a bit more. Whoops, technology is not working. So I will. Okay, I will prepare this. So let me just delete this, and I'll do it again a bit prettier. I'll try this before. I forgot to erase it apparently. Thanks for overlooking. Sorry for not minding this. Okay, so what is it? So M will be some manifold, but it will be a surface in this case. But let's do some introduction now, where maybe you take some kind of basic case. And sometimes you start with the very low dimensional case, and in this case, M is R. And then R is not a symplectic manifold, of course, but T star M is a symplectic manifold. So this is T star M. This is just a plane in this case. And this is the two-dimensional version of the story that I'm telling you about. So there's some kind of motivation. Then I have these curves here that coincide with just what do you call them? Vertical lines outside of compact subsets. Let's take 2 of them, and then they do whatever they want inside here. So I have these 2 curves now. I could do for more. And then you know that these are Hamiltonian isotopic actually to a much simpler picture. And tell me if I draw somewhere where you cannot see. I think you can see everywhere. So I just assume that now. To these 2 straight lines. What are those? Well, these are cotangent fibers of points in the manifold. So those are 2 cotangent fibers. And of course, I can do this simultaneously. I can do this for one of them, but I can also do it for both simultaneously. However, there's one flaw with this kind of baby case. Usually you get kind of the nice and obvious case when you do this for surfaces, say. But here there's one problem, and you will see that later. But I just you can think about this. But remember that of course H1 of M is 0 here. Let me say H1 of R with R coefficients is 0, of course. And that makes Hamiltonian isotopies very easy. So of course, if you would like to say Lagrangian isotopy, I could have said that too. But Hamiltonian is even possible since H1 is vanishing with R coefficients. However, compactly supported H1 is of course not 0, and that means something here. Namely, that means that I cannot do this compactly supported necessarily. Of course, there could be some kind of area between here that is working against us. But anyway, so later I will move on to 1 dimension above, or 2 dimensions above, to 4 dimensions, and then it will be good to know that also this is in high dimensions then. Sorry. So anyway, so of course there is some kind of area considerations here, and if I'm not lucky, then I would actually have to push things all the way up to infinity between these 2 lines, because maybe these 2 lines are like this. So I need to kind of to do something radical there. But okay, so this will not be a problem in high dimensions. So this is the baby case in some sense, but in some other sense it's a bit degenerate. So this was some kind of cartoon motivation for what the question is about. So any questions about this, feel free to stop me. Well, otherwise I'll move on. So now I will continue before the result, I will describe a bit more carefully the setting. In general, well, it's T star M. So M is the smooth manifold, and the cotangent bundle is equipped with a so-called tautological symplectic form. And this is exact, and you write it as d of p dq, but in the picture above here, then of course q is here and p is here. And locally it is exactly like that in all dimensions, but for those who didn't see this, well, we have some, so this is some n manifold, smooth n-dimensional manifold, and then we have local coordinates and then we have induced coordinates on the kind of conjugate coordinates on T star M. And what is that to say? Well, every one form can be pointwise at least written as some canonical quantities if you have these coordinates qi fixed. Then locally everything is like, you just have to specify the p's. And that's also gives rise to actually a one form on T star M. So any kind of one form can be written as this, but then a bit confusingly sometimes. But if I now see this as a one form on T star M instead, then the symplectic form is, yeah, this exact form. And in local coordinates, it's just this linear form. So this will be an important examples, of course. T star Rn, and this is now the standard symplectic vector space. So this is an important example. So if you didn't see any other symplectic manifolds, I think probably all of you did, but anyway, this is something to keep in mind. Okay, so what do we need more? We need also another concept. So we now have an example of a symplectic manifold, but we also need the Lagrangian submanifolds. And for instance, if you take the zero section in the cotangent bundle, or you fix a point and you take the fiber, these are prime examples of Lagrangian submanifolds. And this is the same in this case, where this symplectic form is the same as that this PDQ, the primitive of the symplectic form, pulls back to a closed one form, and it's an, should have started with this maybe, that it's a half, maybe I will write it so it's an half-dimensional submanifold. So that's the Lagrangian definition of a Lagrangian. And the Hamiltonian isotopy, I will only present it in the following neat way, if you have an exact symplectic manifold at least. So instead of defining what a Hamiltonian flow is, I hope that those who are symplectic geometry should know this anyway. So for others, then you can think of it as follows in this set. So we will be interested in considering these Lagrangian submanifolds up to Hamiltonian isotopy. So what is this relation? Well, a compactly supported isotopy, say LT, so some Lagrangian varying in a symplectic manifold. So usually call this a Lagrangian isotopy. So at every time it's a Lagrangian submanifold. This is generated by an ambient Hamiltonian isotopy. If this one vanishes. Oh, sorry. So okay. So let's forget about. I just said an ambient Hamiltonian isotopy. I didn't. Let me not say anything about the compact now. But anyway, so this homological condition makes it possible to find this Hamiltonian, whatever it is. I will not use it for anything today, so I will just use the word Hamiltonian. Sorry, it's an important concept, but on its own and so on. But so this thing is called then a Lagrangian isotopy. So for what I will do today, when I will talk about classification and unlinkedness and so on, up to Hamiltonian isotopy, it will be this Lagrangian isotopy relation that I will mainly have to worry about. I will just need, I need to make sure that I can construct an isotopy through Lagrangians, that is. So it's something less to worry about, at least. Okay, so those were the main definitions from basic symplectic geometry that I wanted to use here. So are there any questions about this? Yeah, usually when you give talks on Zoom, there are not so many questions, but feel free to ask. Okay, so I move on then to the results. Maybe then there will be some questions. So the theorem that I will present today, that me and Laurent proved, is the following. So if M is an open Riemann surface. And if L is a Lagrangian submanifold, which coincides with some fiber outside of a compact subset, and say proper, maybe if I present it like this, but in fact, for simplicity now, let's this is the way we phrase it in the paper as well. This can be dropped, but this takes some. It's a non-trivial result that this condition can be dropped. But let me add this in some different color, maybe gray. Let's see how this gray looks. Let's say it's a plane, but that's how we phrase it in the paper. If you want to remove this assumption, then you would have to maybe say exact instead, and it's a non-trivial result, but it's not impossible to prove it, I think, if you have some Floer theory knowledge. Okay, so now let's say that it's just R2, but it coincides with this other plane. This thing here is also plane, of course. This one here. All right. Then L is compactly supported Hamiltonian as topic to T star to the fiber itself. I mean, this is an R2 in this case. Okay, so that's the main theorem. So now maybe it's a good time to ask questions if you didn't understand some words, or if. But yeah, if you're a symplectic topologist, maybe it's not such a complicated thing to understand. So I will. Yeah, no, I hear some question.
Georgios, just a sort of maybe a question that's a bit too specialized, but the question is, suppose you look even in a more general situation in higher dimensions, is it already known that a Lagrangian like the one you talk about, the one that looks as a fiber outside the compact set, is the same as a fiber in the Fukaya category sense? Because you can include.
Yeah. Well, if it's yes. Yeah. If it's so some. Let me maybe can I move this thing to the. I should be able to know. Let me do this as some kind of parenthesis here. So let's make it a bit. Yeah. So let's make it just. So what can you say a priori about this? So let's take T star Rn. Otherwise, it's a bit more complicated. I think you cannot find T star M in general. You cannot find it in the literature. So let me just say something about T star Rn, but it's you can say the same thing in all cases. So this is this is open. So this whole thing here is subcritical, and that of course makes it very, what should I say? Many things vanish there, Floer theoretically, and therefore we can prove many things. That's maybe not a general principle, but let's say it like that. And let's say we have some Lagrangian here, and this is so fiber outside of compact. Well, we can actually say quite a bit if L is exact, because if L is exact, then Floer theory, just Floer homology, even not for chi categories or anything like that, says that L is contractible. Well, you have to use local coefficients, of course, and things like that. So I don't know who to attribute this to actually, but I know that we have proven this with the Cthulhu homology, me with collaborators Paolo, Baptiste, and Roman. But probably this was proven in many places. We even know that this is, yeah, we know something about what happens when you look at the diffeomorphism induced on the sphere at infinity. So let me at least attribute this to Coleman Smith. So this is maybe good to say in connection to this, that we know quite a lot about the topology of L. This is Floer theory, and diffeomorphism type is more complicated. But of course, contractible means that it's diffeomorphic to a disk in high dimensions. But you can ask about what happens if you attach a handle along this, and you get actually a standard sphere in many cases. But this you can find in the literature, but the open condition on the M is important here. But this doesn't tell us so much about this isotopy class. So isotopy class in T star Rn, the isotopy class is not so interesting. But let me get back to that question. But before I go back to this isotopy class, I will tell us something that is known actually. Very strong result. Did I answer your question, by the way, in some way?
Yes, in part. So I mean, I think one part of what you say is very important is that you have this M open, and if it's not open, probably
yes.
things are very different. So
yeah. For instance, yeah. so let me just you will say, oh, of course. I mean, take T star. Yeah, what should I take? T2. Then take a fiber and then connect some with zero section. That's
yeah, exactly. So then
that's,
wait, but I'm confused.
Yep. So, I heard. I think Denis was confused, but I didn't hear what he was confused about.
He froze.
Yeah.
Denis, for a moment.
Hopefully not because of the confusion.
Not because of your computer, but
no, from the confusion maybe.
The statement above that L is isomorphic to R2, is that an assumption or a conclusion of the theorem?
Sorry. So the theorem is proven. We say R2, but I was sloppy here. So to state the theorem, let me state the theorem, because otherwise I would need to. So let's state the theorem like this to make sure that you follow what I'm saying. Let's say that it's an assumption of the theorem. Then my claim was that I can weaken this assumption by saying exact instead and proper. Is it better? But if you read the paper, you will not find this. But I think maybe it's a nice thing to think about and consider as well. But I didn't really want to emphasize this. But since I know that many people like Floer theories and so on, and this is a consequence of Floer theory.
Wait, and in the non-exact case, there are things which are not R2s?
Yeah, non-exact, it can be anything. I mean, you can, if you say orientable, then I will have to think probably, but just take some. I mean, this is what.
Orientable, but okay. Anyway, that's okay. Fine.
Yeah. If you say too many things, then I will have problems. But yeah. Orientable already is probably. Maybe that's a theorem as well, but I don't know. It's good questions. Think about it during the talk. Maybe you can figure it out.
Can I
anyway.
also ask a question?
Yes.
So if you take the zero section and the fiber, and
Yep.
then you do an exact surgery to it, is it
Yep.
obvious that this is Hamiltonian isotopic to a fiber, or is this like?
Yeah, but it's not. Yeah, so then it shouldn't satisfy the assumptions of the M is. It depends what you mean here with M, of course, but you should understand it. Yeah, if you interpret these words correctly, I think it should not be covered by the theorem.
Okay.
Good that you're asking. But okay, but M being not a closed manifold is very important here. Otherwise, I would have to really rethink what I'm trying to say at this moment, at least. All right. Let me tell you some previous results. So when M is R2, this is pretty old now, but it's a very strong result by Eliashberg and Polterovich. So Leonid is here today from 96, if I'm correct. And our proof is definitely, well, in some sense, a bit parallel, but we use different techniques. So it's parallel, and in some sense, the conclusion, part of the proof is very, very similar. And the main kind of tool that is used is similar, since it's pseudo-holomorphic foliations in some sense. But they use something that is a bit more tricky, and we didn't manage to prove the result with their techniques in high dimensions. So you need some kind of embeddedness control for, of course, I mean, you even need a foliation in the end, but you need to control things and make sure that they are embedded. And they use pseudo-convex surfaces. Pseudo-convex hypersurfaces. And we use kind of SFT compactness and finite energy curves. That's maybe now it's a very technical part of the proof here, but this I will not get into that much at the end anyway, but this is the main difference, I would say, that in order for them to say that some disk is a part of a foliation, that this disk cannot become messed up in some way, they need to make sure that it has boundary inside some pseudo-convex hypersurface, and actually two of them. Whereas we will not work with these disks, we will work with planes, and they will be asymptotic to geodesics on some Lagrangian, and that makes it easier. So that's a small comment of a very technical nature and very crucial, but maybe that's somehow the main new part of this story in some sense. So now I'm scrolling down here. Tell me if you want to see something again. Another interesting result in connection to this is when M is Rn minus a point. That's the next simplest case, I suppose, after Rn. Then when n is greater than 3, then the homotopy version of the statement is first of all, the homotopy version of the statement is trivial in the surface case, because there is well, compute homotopy groups. In high dimensions, it's non-trivial, because pi n of Sn minus 1 is non-trivial in high dimensions. Anyway, but homotopy version statement is true also by Ekholm and Smith. So that's also, this is a highly non-trivial statement, and very far from what we are doing here in this theorem, of course, because Hamiltonian isotopy in particular is a homotopy, but it's very difficult to go the other way around, as we know. But in high dimensions, this is all we know, actually, when m is Rn minus 0. So we know very little there. But anyway, it's a non-trivial result here. And very interesting. Yeah, I think that's all the background that I want to say. So are there questions? Sorry, all the previous results that I want to say, that I want to mention. But okay, so now what we actually were interested in was the word in the title that says unlinkedness. So you could think that we were inspired by the Ilyashvili-Polterovich result from all the way back from '96, and that we were wondering, why can't we prove this for higher genus surfaces? That was nice when we realized that we could actually do that. But the initial reason for looking at this was that we wanted to show something for unlinkedness. So this is the original interest. And this is if you have some multiple component Lagrangian, and if you embed this into T star M, and so this is a Lagrangian link then. And let's say now that Li are coinciding with the, diffeomorphic to R2s, and coincide. Let me do this a bit like this, so that this all of these coincide with some T star of different points outside a compact subset. And yeah, so we were actually thinking about R2, but we were thinking about many Lagrangians, many Lagrangian planes. And the corollary then that was our main interest in the beginning was that, well, say now that here M can be possibly closed surface, but say that L1 is actually isotopic to some fiber, or you can drop this assumption but assume that it's open instead. But let's say it like this. Then the link is compactly supported Hamiltonian isotopic to just this standard unlink, say, just a collection of fibers. So this is a corollary, and the only thing you have to observe is that if I remove a fiber, then of course it is an open, sorry, if I remove one fiber, this is the same thing as taking the cotangent bundle of the complement of the corresponding point. And this is open. So, okay. And then inductively apply theorem to L2, etc., etc. Okay, so the main point here that I want to make is that we get this unlinkedness result from the main theorem, because whenever you have when you remove a fiber, you remove a point. So you start with R2 perhaps, but then in the end you're left with R2 minus a bunch of points. So okay, so this was our first initial consideration actually, but then it turns out that you can also add some genus and so on and get this theorem. So are there questions about this? Right. So that is what we proved, and then I will go on to discuss some things that are not in the paper really, but another kind of motivation for this linkedness consideration is something from smooth topology. So let me see here now. So some motivation from smooth topology. So let's say alpha is a now I write this a bit weird maybe since I had these coordinates, but I will need it later anyway. So let's say this is a linear one form. So Q1 naught up to Qn naught, they are just numbers. dp1 up to dpn are linear one forms on Rn, but so now P is a coordinate on Rn. I think this choice, let me call this alpha naught, this choice of notation for my coordinates will hopefully seem justified soon. So observe that the graph of a one form which coincides with alpha naught outside of a compact subset is an embedded plane in T star Rn, which coincides with, I don't know, coincides with okay, let me write like this to make it Q naught, the fiber over Q naught outside or compact subset. So all I'm saying now is that, well, these are examples of Lagrangians that satisfy the assumptions or part of the assumptions of the theorem. Right? I hope that's clear. Well, almost. Okay. So the Lagrangian condition, if and only if it is closed, that is also important here. And to check this, I should say maybe that the symplectic form is d of p dq, but it is also, of course, d of minus q dp. So yeah, you can kind of exchange the fiber and the base up to sign here. All right, so this is one way. So Lagrangians that we care about, they are, for instance, obtained in this manner. And yeah. Sorry here, oops. So unlinkedness of such Lagrangian, so a graphical Lagrangians is known for L inside, oh no, I don't remember which dimension, but say high n. Inside Rn. Well, why? By Serre's pseudoisotopy theorem. Well, n equals to 2 can also be proven then by Smale's fact that the diffeomorphisms of D2 are contractible. So in this case, so pi k of diff of D2 is contractible. Right. So let's try to just understand this here. What am I saying? Well, I'm saying that if I consider L Lagrangian inside the cotangent bundle of Rn minus the origin, if that's graphical, so let me put some fancy color there. If it's graphical, then that's the same as a closed one form that is non-vanishing and which coincides with this linear form outside a compact subset. And that can actually be interpolated through such closed one forms to just alpha naught. But this is a highly non-trivial theorem in smooth topology, which is Serre's pseudoisotopy theorem. So if you don't get what I'm saying, or if you're interested in to hear more about this, then if you don't understand the connection, then please ask me. So this pseudoisotopy theorem usually is presented in the following Morse theoretic way, that you have a Morse function without critical point actually, and then this is like this is the function that defines the primitive of the one form, and you can actually find a path of functions without critical points to the standard linear function. So this is the pseudoisotopy theorem. So you see now, I hope I managed to convince you that there's a connection here. And then one last word about this is that, well, we don't prove anything actually for higher homotopy groups, higher connectivity of the space of Lagrangians. I would suspect that if you just look at all the points in our proof and put a parameter, that you will be able to do this too, but we didn't dare to do this yet, at least. In fact, I should tell you that in R2, this is a much stronger result. So Lashper and Polterovich, they prove this for all pi k's, meaning that also a family of planes is trivial up to Hamiltonian isotopy. So the strongest result you can imagine. And the point I want to make now is that in high dimensions, we can actually prove that this contractibility cannot be the case, at least for in this Rn minus the point. There exists non-trivial families of pseudo-isotopes. So we never go to high dimensions, but if we do go to high dimensions at some point, or if someone else does it, then perhaps the classification will still be the same, is the hope at least. Who knows how to prove that? But observe that there are some interesting features in high dimensions, namely non-trivial families of such pseudo-isotopes. Or pseudo-isotopes, or same thing as non-vanishing one forms. Closed. And then if you go to pretty overlooked old paper by Eliashberg and Gromov, you can learn that generating family methods can actually tell us that this is also a Lagrangian phenomenon. Let me not make this precise, but through sectional, sorry, not only graphical Lagrangians. So it's you could ask the question. So the way I like to think about this is, of course, an old philosophy, perhaps due to Arnold, I don't know, about questions in smooth topology, when you suddenly relax the question and go to the symplectic topology instead. For instance, can I find a path of closed one forms that are non-vanishing? You can relax that to saying, can I find a path of Lagrangians that do not intersect the zero section? And in many cases, we expect the answers to be the same in two cases. And for that reason, maybe this Smale's theorem about diffeomorphisms, or the pseudo-isotopy theory in high dimensions, that makes us believe that there is no Lagrangian linkedness in high dimensions. In dimension 4, then we prove this.
Sorry,
so that's Smale's result in some sense. And sorry.
So your base manifold M is what? So when you are talking about
in this basic case, then M would be Rn minus 0.
So you are discussing the results about forms also in the case of Rn.
Yes, exactly. So the other, when you change M to something that is not Rn, then the question is, of course, a generalization of the pseudo-isotopy theorem into a different way. That doesn't really make sense, maybe, but because so forms on Rn make sense, but I don't know what the form is of a
take a fiber in. There was old paper by Sikora which addressed exactly this question. Yeah, so you have a form without singularities on a higher dimensional torus, and whether you can deform it within the given cohomology class to a linear form. And the answer is no. It was kind of.
Yeah. So this is also related. This is related to this question, of course. So on the torus, there's a problem now, or no, there's a problem. It's a bit more difficult because the form then is not exact. So the Lagrangian is not exact anymore. This is also interesting. And actually, me and Laurent, we were looking at linking for tori too, but I'm not talking about that today. But since you mentioned this, then I just want to stress that this paper by Eliashberg and Gromov, it's for exact Lagrangians. So the good thing is, if you take this fiber, it's a plane, so it's exact. So the one form is actually closed. But yes, that paper by Sikora is also very relevant. It's a similar question. Are you happy with that comment? All right. So you can see this as some kind of generalization to this smooth isotopy. But then, of course, there is this highly complicated space of pseudo-isotopies, and then it means that they're also interesting. This is a theorem by Eliashberg and Gromov, then, that also it remains interesting if you drop the graphical condition and just talk about Lagrangians. That's the outcome of that. All right, let me see how I'm doing with time. So I don't have so much time left, so I should start with the final part. So if there are no more questions, then let me move on to describe the proof. So, now, as in the assumptions, we have a Lagrangian that is a plane, coincides with a standard fiber outside the compact subset. This is an open Riemann surface, and that means that I have, let me see, no, this is not Y2. This is, sorry, this is Y2. So M is actually not exactly this plane here, because I can have genus. So it can look like this, for instance. So this is M now. So there's some big part there where I will need coordinates y1 and y2. And here is some point, the origin in this coordinate system. But so say L is equal to T star above the point outside compact subset. Right? So this is how it looks now.
Georgios, I'm
yes,
sorry.
Question?
Y and Y1 and Y2 are coordinates on what?
Yeah, so it's an open subset. So this is a subset of M. Then there is some. It's not a planar domain, but I draw the image here as an immersion in the plane. So M is kind of immersed in the plane here. That's what I'm trying to say. Maybe this is M here. So this is what I'm trying to.
So you fix an immersion of M into the plane.
Yeah, actually, I just need to speak about coordinates y1 and y2 here. But yeah, so let's say that M is as I drew it here, immersed in the plane, for simplicity. Well, what I want to fix some subset here, and say where this coordinate is greater than -1, and then I have something that is R, and let's see here, y1 times some half infinite ray here, y2, and then times, sorry, this is messy, and then times R2, x1, x2. So these are the coordinates, and so what is what here? Of course, y1 and y2, there are q's, and these are p's. But observe here that I also have like the symplectic form. I call this x. The later coordinates are x's because the p wedge dq is then dx wedge dy. Right? So I get the standard linear form there that I'm used to. So it's easier to remember this convention, I think. Okay. Then I need something here that is important for the proof. So yeah, time is not on my side as usual, but anyway, so I will try to draw some pictures and tell us what the construction is about. So Q naught does not make sense when you have L, but say if you would have the standard fiber, then I want to construct this hypersurface Q naught in the case when L is arbitrary. But what is Q naught? Well, Q naught is just y2 equals to 0. Oh, sorry here. R times y2 equals to 0 times R2. So it's a hypersurface. It contains this fiber over the origin, but it's a hypersurface. It's not a Lagrangian, but it contains a Lagrangian. And the goal is to construct such a hypersurface. This is very imprecise, I know. I will soon give the precise meaning of this, what it means, such a hypersurface. And the goal is to use this for unknotting. But before I tell you what we really want this this hypersurface to satisfy, let me just make some important points here, namely that this Q naught is foliated by symplectic, of course even pseudo-holomorphic if you choose J appropriately, but it's foliated by these obvious symplectic planes. And let's see now, which did y2 is fixed. So R times T, maybe I want this to be an S, times R sorry, this was not S, this was a 0, times S. So y2 is 0, x2 is fixed, S, then I have a symplectic plane. And it's foliated by those. And that's the same setup as in Eliashberg and Polterovich paper. And the same idea is to reconstruct this by using pseudo-holomorphic foliation techniques. So I hope you have a good picture now of the standard case, the unknotted case. So let's move on a bit to what we want to actually require. We want a hypersurface Q such that first property, Q should be foliated by symplectic planes, sigma L's inside Q, parameterized by R, and then of course some assumptions. The sigma L should coincide with this standard plane that I just, so sorry, I shouldn't have used S, I should have used L, or I should have switched something here. When x2 is fixed and y2 is 0, I have a symplectic plane inside Q naught, and I want it to coincide with that plane. It should be equal to such a plane for all L sufficiently big. And that's the foliation that I want to see in Q. Then, of course, I want it to interact with L in some particular manner. namely, I want L to be contained inside Q. That's all I want. Well, not exactly all I want, but in this second property, that's all I want. In the third property, I want the foliation to interact in a very particular way with L. And since my time is very close to finishing, I will not have time to introduce the parallel transport, but I do want this parallel transport. So let me say something about that in words. Since there's a foliation, and since there's a hypersurface, so let me say just induced by the characteristic foliation, then there's a transport map, basically just the connection defined by the characteristic distribution. This is a symplectomorphism from one fiber to another. And we want this to preserve the foliation y1 is equal to s. So sorry, that was the s. So I have to change my slide above there. Okay. So this is the foliation by lines in and one of these will kind of be the fiber. Okay. So this is the goal. So exactly how many minutes am I allowed to take more? Octav, do you have some?
You can take I don't know, 5 more minutes. After that we have discussion time, so you can take a few more.
That sounds good. Okay, very good, very good. So at this point, okay, so I want to make some comments first about what if you get this Q, what happens, and then I will end by saying, drawing a picture at least, drawing a picture of how we get this Q. But first, if you have this Q, what is difficult? Well, this condition here is actually, I will not tell you how to arrange this, but in fact, this condition here is soft techniques. And this is the key word here is the symplectic suspension of a Hamiltonian. So namely, if you look at this hypersurface Q, you actually have enough room to deform it to make this P3 satisfied. So if I can make P1 and P2 hold, then P3 is kind of, it's not for free, but it's, you use soft techniques to achieve 3. So P1 and P2 are actually difficult, and I will end by saying how to do that. But let me just now say very quickly now that if you have this P1 to P3, then you can actually quite easily construct a Lagrangian isotopy. And the reason is that Q is foliated by standard at infinity planes. Plane standard at infinity, I should have said. So that Q is foliated by standard at infinity planes, you can just look at the fact here that the parallel transport preserves the foliation, and then you can get it. But sorry, this is not a difficult point, but I recommend those who didn't see this to study a bit hypersurfaces in symplectic manifolds and Lagrangians inside hypersurfaces, and to see that this technique is very useful. So the proof is done if you just can get P1 and P2, and this is the difficulty, and also the difficulty for Ilash-Polterovich, which the other parts are following the same lines actually. But P1 and P2 is kind of difficult, but it's also very, it uses kind of technical stuff like SFT compactness, but it's a quite short proof. So let me choose the correct picture to draw here the last minute. Yeah. And okay, so let me see here. I have to skip my notes, and it takes time, of course. Okay, so let me try to draw some pictures here. So how to get P1 to P2. So the point is that if I dig a hole inside Q, I can make P1 to P2 satisfied outside of a compact subset, meaning just that, I mean, this is obvious. I can just take Q naught there, but then of course there's some point where I cannot use Q naught because my L is not standard. And what I want to do is that I want to extend this kind of foliation near L. This I can actually do because I have my L here, and it's standard outside of a compact subset. Then it's doing something that I have no idea whatsoever what it is. But I can take my sigma L here, and then I can at least extend it to not a plane anymore, but something else. I can just follow this. Oops, and I have to follow it. I do not know how to extend this to a plane. I can do something like this. I can do a bit better. I can close it up like this. So now it looks a bit weird here, but okay. So this is the hole here. So this is so outside here is sigma tilde L. So this is a, here I don't know how to, I don't have any coordinates that tell me that I can fill in this with a symplectic plane. But of course, for L very, very big, then this Lagrangian is no longer knotted, and I can take this standard sigma L. So what is left now is to fill the holes. Oops. Then fill the holes. So there are two holes here. Look at this picture here that I have this component here and this component here. And if I manage to fill those in by symplectic planes, they cannot be flat. They have to be knotted in some way, or maybe not knotted, but they have to be a bit, yeah, complicated. If I manage to do that, then we get this sigma L. But here we need some powerful technique, of course, because there's nothing that tells us that this can be done. There's no smooth topology that tells us that symplectic disks, embedded symplectic disks exist, and then we use pseudomorphic foliations. But then what do we do? So we introduce. So now is actually the main point where our proof differs from Elash-Propulter-Rovischer's proof, and in some sense it's making it easier, I would say, because it's a very short proof in some sense, but it builds on these highly technical SFT techniques, of course. So we introduced an auxiliary Lagrangian, and I will draw it here. S1 times R, and you need two of those, in fact. And what is that? Well, that is the boundary here. I should have used this green here. Here you see an S1. here, and then we extend this. So we introduce it, and then we remove it, which is a bit funny. So let's call this some curly L1, curly L2. Here we have a concave cylindrical end. And then we use the pseudo-holomorphic finite energy pseudo-holomorphic plane techniques to find, construct foliation. Let's say these words mean something to the experts only, but finite energy foliation by pseudo-holomorphic planes inside this manifold. Asymptotic to these LIs. And we're in a good position because at least we can do this for, here is L. If I consider sigma L with L very, very big, say, then I have these two Lagrangians, and I have this finite energy plane C here. It looks like a disk, but when I use this cylindrical almost complex structure, this is actually conformally not a disk, it's a plane. And these two planes here, they foliate locally a hypersurface, and then SFT techniques use SFT techniques. That only, so many of the techniques, of course, like compactness work in all dimensions, but now we have to use techniques, well, in this four-dimensional setting to get the embeddedness and even foliation properties to hold. And that's the story. So I know I didn't have so much time on the end here, but at least I want to say that my ambition was to convey that the proof is actually, the idea is very tiny somehow. So it's the SFT will do most of the job for you in the end. So it's a very simple proof. Maybe it's not good for the paper if I say it's too simple, but anyway, that's also nice, I think. So thank you very much. That was all I had to say.
Right. Thank you very much, Georgios.
Thanks.
So, please ask. It's a moment to ask questions if you want.
I have the chat here, I think. Yes, I do, but feel free to.
Without chat, I mean, we can.
Yeah, probably people who can just. Maybe someone is shy.
May I ask a question? So I did not understand how these curly L's sit in the cotangent bundle. So what's the geometry? Given that your Lagrangian thing is the formation of a fiber, so how do you put?
Yeah, that's good point. So if I go back here, maybe so this looks very complicated, this picture, of course. How can I make sure that this is happening there? But okay, let me say that it's a very important point. It's not complicated at all. It's just saying that if I take T star M, and then I let's see here what I want to say. I want to remove a big subset. No, so what I want to say. I want to say that Okay, so let me say like this instead.